Hey everyone, and welcome to today's Explainer. We're going to take a super fascinating chronological journey today to demystify the complex, basically invisible machinery that keeps us perfectly comfortable every single day. I mean, we spend so much of our life indoors, right? And we're totally reliant on this system hidden just behind our walls and ceilings. So today, we are tracking the evolution of HVAC systems, starting from ancient methods of simply moving air and harnessing fire, all the way to the highly sophisticated, modern electric technology that defines how we live and work today. Let's get into it. But first, before we time travel back to the origins of climate control, we really need to answer a fundamental question just to understand what exactly we're building here. What does HVAC actually stand for? We hear this acronym literally all the time, tossed around by technicians, homeowners, everybody. But breaking it down actually reveals the true scope of what these systems are really designed to do. All right, so HVAC stands for heating, ventilating, and air conditioning. The absolutely crucial point here is that this acronym represents a complete trifecta of indoor comfort. It's the transition from ancient, totally separate methods into one unified modern system. It's not just about, making a room hot or cold. It's a completely integrated approach. Heating, ventilating, and air conditioning all working together in perfect harmony to improve your overall indoor air quality and give you total environmental comfort. So here is our roadmap for today. Number 1, what is HVAC anyway? Number 2, from fire to steam. Number 3, the accidental air conditioner. Number 4, the electric cooling boom. And finally, number 5, how modern systems work. Okay, section 1, what is HVAC anyway, beyond just hot and cold? Let's start by looking at what total air conditioning actually entails today. Way back in the 1880s, refrigeration was basically just for freezing meat for transport and making ice. But true modern air conditioning, it requires the total control of 5 vital environmental elements. First, temperature control, obviously. But second, you have to manage the moisture, the humidity. That's what makes a hot day feel truly oppressive, right? Third, you must supply outside air for ventilation so things don't get stale. Fourth, filtration of airborne particles for your health. And fifth, the actual movement of air within the occupied space so everyone feels it evenly. You literally need all 5. And when you look at the core components of a standard system, it brilliantly illustrates how this all comes together. You've got things like the evaporator coil, the air handler, and the condenser, all working in tandem to achieve those 5 aspects of indoor air quality we just talked about. Notice how the system is divided. You have a fan and compressor usually sitting outside, pushing refrigerant through tubes. Then inside the air handler, there's a blower, a filter, and that evaporator coil. The indoor air gets cold from your rooms, passed over those highly engineered coils, filtered, and then pushed right back out. It's this continuous closed-loop cycle of comfort.
Moving right along to section 2, from fire to steam, early engineering innovations.
Now that we know what modern systems look like, let's take a massive step back in time. It is actually incredible to realize that the foundations of modern climate control stretch all the way back to ancient Rome. They utilized central heating for their public baths and even built wind towers to naturally cool their homes. Fast forward to the Industrial Revolution in the 1820s, and a British engineer named S.A. invents the steam radiator. Then, in 1851, we get this massive leap, an early air conditioning patent by a Florida physician named John Gorey. And get this, he didn't invent it for comfort at all. He actually used ice-cooled air to fight the spread of infectious diseases in hospitals. To really give you an idea of the Industrial Revolution's impact, just picture those early, bulky, central boiler steam systems used for heating before forced air furnaces took over. The sheer size and heavy iron construction of these units was wild. They used a massive central boiler to heat water and distribute steam throughout a building via a huge network of pipes and radiators. Just imagine how incredibly loud and swelteringly hot the basements housing those iron beasts must have been. But hey, it was a huge leap forward from relying on localized fireplaces, and it finally allowed for an even distribution of heat across large spaces. Now, these early steam systems eventually evolved into 2 main categories based on pressure. You had low-pressure steam systems operating at no more than 15 psig, and high-pressure steam systems operating above that. But operating these required immense care. Think about this for a second. When water boils into steam, it expands to about 1,600 times its original volume. 1,600! Because steam has the capacity to expand at such high velocities in all directions, poor boiler operation could be a literal disaster. That's exactly why strict engineering codes had to be written, to manage this incredible force and basically stop things from blowing up. All right, Section 3, the accidental air conditioner. Controlling humidity, not humans. So now we reach the dawn of the 20th century. In 1902, Willis Carrier invented an apparatus for treating air. But here's the crazy part. It wasn't meant to cool people at all. It was actually built to remove moisture for industrial yarn manufacturing. You see, managing humidity made yarn a lot easier to work with. Carrier realized that as his machine removed the moisture, it actually cooled the air as a very, very lucky side effect. Without even meaning to, he completely revolutionized the industry by showing that electricity could be used to mechanically manipulate indoor climates.
35,000 cubic feet of air circulated per minute. That is what it took to cool the Missouri State Building at the 1904 St. Louis World Fair. The public was absolutely stunned. I mean, it cooled 2 whole floors of the building, and nobody at the time could have imagined something like this was even possible. It was a true wonder of the age. Well, until November of that year, when the system's boiler exploded and unfortunately set the building on fire. So, yeah, proving that safety and refinement were still major hurdles. Section 4, the electric cooling boom, entering the American home. Despite that fiery setback at the World Fair, innovators kept at it. They kept refining the technology, downsizing it from those massive industrial plants. By 1931, the window air conditioning unit was invented. It's actually fascinating to realize that the modern air conditioners sitting in our windows right now are still based directly on this legacy technology. As the machinery became smaller and much more manageable, it moved from factories and movie theaters directly into the hands of the public, and it completely changed the way people lived during the hot summer months. Then, post-World War II, this electric technology just exploded into the mainstream during the 1950s housing boom. A really huge milestone occurred in 1956 when Carrier won a major contract to provide central air conditioning to 700 upscale Pennsylvania homes. By the 1970s, this kind of central air conditioning and ventilation had become totally standard. It completely paved the way for the seamless central air we all just expect as a baseline in our homes today. Which brings us to Section 5, how modern systems work. The mechanics of heat transfer.
Okay, so we've gone from Roman fires to window units. But how do the really advanced systems actually function today? To understand this, we have to compare the 2 main mediums used to move heat, steam and water. While older steam systems had incredible heat transfer and could automatically adjust to balance loads without needed supply pumps, modern engineers often prefer hydronic or water-based systems. The crucial point here, safety and precision. Because water doesn't expand violently at high velocities like steam does when it boils, it's vastly safer. Plus, water allows for far more precise temperature control, since you can easily modulate its temperature before it ever reaches the room.
All of this thermodynamics builds into an absolutely incredible piece of modern machinery, the evaporative cooling tower. To really grasp the genius here, let's walk through the 6-step process. Step 1. Hot, 95-degree water is sprayed down onto a surface called fill. Step 2. That water coats the fill and flows down to a sump. Step 3. Air enters near the bottom and rises up. Now, step 4 and 5 are where the magic happens. The descending water evaporates into that rising air, and that latent heat of evaporation actually cools the remaining water left behind. Finally, step 6, that freshly cooled water is pumped right back to the chiller. It literally uses its own evaporation to chill itself without requiring external energy to remove that heat. How cool is that?
And that brings us to the end of our journey. From ancient Roman fires and wind towers, all the way to Willis Carrier's accidental yarn cooling machine and the brilliant thermodynamics of modern hydronic systems. I really hope this explainer leaves you marveling at the incredible mechanical evolution required just to keep us perfectly comfortable. The next time you simply put